Are there any questions before we begin? Okay, I'm not sure if you had a chance to think about the problem from yesterday. Let me repeat it again. So this is lecture 12. So what we ended up trying to do last time was just finding the derivative of arc sine of x. So it was last time we were trying to find the derivative of y equals arc sine of x. Okay. And so the idea is that, again, arc sine, that's the inverse function to sine of x. So when you try to find the derivatives of these functions, you have to take advantage of the fact that you know the derivative of sine. Okay. So we have to make somehow the sine function appear on this equation. And the easiest thing to do that is to take sine on both sides of the equation. So if you do that, you get sine of y equals sine of arc sine of x. Okay. But then the point of it being the inverse, the point of sine and arc sine being the inverses of each other is that when you write them next to together, like as in here, they kind of like go away. So they disappear. And so you're just left with x. Is that making sense so far, so good? And the reason for doing that is that you do know the derivative of sine. So what you want to do next is just take the derivative on both sides with respect to x. Now to find this term, the thing is that sine, the way it's written down is in terms of y. So to find this derivative, which is with respect to x, you cannot just compute the derivative directly. You have to use the chain rule. So you can write this as b sine of y. And then the other one is easy because it's the derivative of x with respect to x. Again, like the nice thing about this notation is that it does behave almost like as a cancellation of fractions. So you can like basically cancel the two terms and you get one. So that's why there's a one here. And now everything else is more or less straightforward. So the derivative of sine, remember, is cosine. So you put here cosine of y times dy dx equals 1. And that allows you to solve for the derivative. And you get 1 over cosine of y. Is that making sense? Any questions up to this point? Uh, so this is more or less this is the correct answer. The only thing is that it looks a little bit weird because here at the right-hand side is in terms of y, and we want the answer to be in terms of x. So we want this to be in terms of x. So how do we do that how can we put that in terms of x? Well, what is x? X was, or x is sine of y, okay? So there's like a couple of ways to do it, like maybe the more geometric way, which is convenient. If you remember the definition for the sine, let's do it that way. It can be maybe easier to understand. If you have an angle y, so instead of calling this angle theta, we're just calling it y, but everything else is the same. Okay, so if you remember on the unit circle, right, if you draw like a right triangle whose hypotenuse is 1, then you have the so secretly this triangle is kind of being drawn on the unit circle. Then that's right. This it looks a little bit weird. This side would be sine of y, right? Because remember the sine is opposite over the opposite. Let's call this. Let me. Okay, yeah, this can be a little bit off, odd just because of the names we're giving to all the letters. So let me write it in a way that's less confusing. So if this is A and B, right, then the sine of y is B over 1, which is just B. So B is the sine of y. Is that making sense? And then at the same time, what's the cosine of y? That's A over 1. So A is the cosine of y, right? But because you have this identity that cosine squared plus sine squared equals 1, which is Pythagoras theorem. So just remember that identity. So 1 squared equals cosine square of y plus sine square of y, which gives you the formula that cosine of y, well, so 1 minus sine square of y is the cosine of y, okay? Sorry, cosine square of y. And so when you take square roots, you get 1 minus sine square of y equals cosine of y. I guess I could have started just with this all together, but like that's like just a refresher of where this comes from. And then just because of the particular names we gave to the variables in this problem, x is being called sine of y. So this becomes root of 1 minus x squared equals cosine of y. So why is that useful? Because the y dx, which was 1 over cosine of y, in terms of x becomes 1 over root minus x squared. But what was y? Y was arc sine of x. So that's how you end up with the formula that the derivative with respect to x of arc sine of x equals 1 over root of 1 minus x squared. So I got, okay, let's see. So is up to this point, okay. So the thing is that in this particular problem, if you look at the very beginning, like this wasn't from the very beginning of the problem, we said x happened to be sine of y. So that's why I'm substituting that x here. So I'm substituting the sine squared with x squared. Does that make sense? Oh, I can keep these two next. So you see, like this is sine squared, but sine of y was x, so I'm squaring both sides to replace it as root of 1 minus x squared. Yeah, it is like what makes this a little bit confusing is the names of the variables. So, but if you so, but except for the names of the variables, it's more or less like the standard stuff. Um, is that okay? Any other questions about this one? Let me see if I can scroll down a little bit just for you to copy it. Now, in practice, like, these derivatives, I wouldn't, it's not that like I'm expecting, like for something like the derivative of arc sine of x, I'm not necessarily expecting you to memorize it. Oops, I did this. So it's not that I want you to memorize this formula. It would be more along the lines of like, I could ask you more like something like, oh, what's it, like find the derivative, um, and to find, or show that the derivative is that formula, and then you kind of reproduce these steps. So for these problems involving the arc sines, these inverses, I'm more interested in you just kind of like repeating these steps than memorizing these formulas in particular, because it's just like they're kind of complicated to memorize, and they rarely appear, so there's not much to be gained by remembering them, by memorizing them, if you know what I mean. So it's more like I'm more interested in for at least these particular formulas, I'm more interested in the process of how you get to them than in you just knowing what it is, like the answer. Okay. So again, I'll give you like a list of functions or derivatives I would expect you to memorize for the exam. I'll write that down, but I won't include this one because I think it's a little bit too much. Um, okay, let's um continuing use in similar problems to this one. Let's just there's a thing called logarithmic differentiation. So this is like again, we're still kind of just learning different tools to find derivatives. If you notice what we have been doing all along. If we get time, today we'll talk about related rates, which is a little bit more of an application for how to find derivatives. But up to now, more or less all our energy has been spent on just how to find derivatives, and not so much on how they're used in practice. We should be done with the material for the exam between today and tomorrow. Yeah, probably half of tomorrow's class. The last topic will be the related rates. So if I started today, I'll probably finish it at the beginning of tomorrow's class. So, once I have probably by tomorrow, I'll write down the study guide for the exam and send it to you. It's more like basically the topics on chapter 3, but from there I'll just tell you what to pay attention to. Um, for today's quiz, I'm giving everyone 30 minutes. So there's again in just in this thing about finding using the finding derivatives of functions. There's another trick to find derivatives of functions, which is called logarithmic differentiation. But for that, we just have to talk a little bit more about natural log, which I reminded you yesterday about it, but I didn't say too much of natural log. So this is more like of a refresher about what natural log is. So again, it is written this is like the name for the function, right? Ln of x. So this is the natural log of x. It is the inverse of the exponential. Okay, so a couple of things. First, like maybe I should actually just give you the graph of it. So this is how natural log is supposed to look like roughly. So it is defined for positive values of x. At 0, it's not defined. It is undefined at 0. But now that we have this limit terminology, right, you can actually say what's the limit as x approaches 0 from the left, sorry, from the right of ln of x, right? So this just means how does ln natural log behave, right? As you choose x, values of x closer and closer to 0, and what the answer looks like. Well, actually, if it were 0, that means that it would, right, if it were 0, it actually means it would stop somewhere in here. If you're right, it's the second option. If you follow the graph, the values for y keep decreasing indefinitely. So actually, the limit is negative infinity. So if you want, you can say that natural log has a vertical asymptote at x equals 0. Is that making sense? And then it does, okay. So there's this spot where the natural log crosses the x-axis. That means where the function takes the value 0, right? And that's the point 1 comma 0. So that just means that this means that ln natural log of 1 equals 0. So let me write it here because this is one of the important values of natural log. So everyone should definitely know the natural log of 1 equals 0. And then there was another important value for natural log that's kind of useful to know, which is that ln of e, the number e is 1. Okay. And more generally, you have like this cancellation property that ln of e to the x is just x, and e, let me use a different color. And e to the ln of x equals x. So in terms of values, these are important properties. So put them in a box. Okay, so again, like what this means is that when like the last two, what they mean is that whenever a natural log sees an exponential or an exponential sees a natural log, they kind of cancel one another. And so you're just left with the variable x. Is that okay? So far, so good. I mean, this is like the last two is essentially what it means to say that natural log is the inverse of the exponential. That's more or less the definition of being the inverse, that this would happen, that they just cancel one another. And then three other important properties of natural log that basically are kind of like the reverse version, like the mirror version of the properties for the exponential. Is that if you have the first, like there are three that you really need to know. The first one is that the natural log of a product is the sum of the natural logs. The other one is that the natural log of a ratio is the difference of the natural logs. And the last one is that the natural log of a power is essentially allows you can just bring down the exponent to the front. So these three are the important properties of natural log you should know. Which again, I mean, hopefully everyone had seen before, but I'm just reminding you of them right now because now we're definitely going to use them a little bit. Is that making sense? Um, so it's so again, there's this way to find derivatives. Oh, sorry, I should have said this as well. It's kind of now one of the key properties of natural log is that we have like a formula for its derivative. So another important formula is that the derivative of natural log with respect to x is 1 over x. Okay, this is like also very, very important. Okay. So there is this way to find derivatives of powers by using by taking natural log on both sides of the equation. So this is what's called logarithmic differentiation. So let me explain what I mean by this. So it's mostly used. It is a way to find derivatives of functions. In particular, it's very useful for it is very useful for formulas which involve taking a function to some power, taking an involve the power of a function or a number. So by that I mean things like things like and I'm about to do these examples so that you see what the answer looks like. So let me put some like 2 to the x. We could also do like maybe 3 to the x squared plus 1. That could also be fun. Let me see. And let's do like at least like 4 to let's see. What else? Oh, okay. Uh, something fun. So if you look at, I kind of writing the expressions in order of increasing difficulty. So if you look at these expressions, what they have in common is like, well, like the first two are some number raised to some variable, like 2 to the x or 2 to the x squared plus 1. So this is like the more, or I should have said like some number raised to some expression of x. So it could be 2 to the x or um 3 to the x squared plus 1. And the last two are even more complicated than that because it's like something that depends on x raised to something that depends on x, something that depends on x raised to something that depends on x. So things, and for these problems, I'll tell you that you should use natural log to find the derivatives. So it's not that I would keep that a secret, but it's like usually the way to, if you were to identify them, the way it looks like it is, it involves powers of like the variable x. Like the function is like a combination of like, it's like something that involves like a variable raised to another variable or things like that. Or like a power, like an expression of x raised to an expression of x, or like something where the exponent is depends on x, basically. So here, in all of these, maybe I should put it like that. In all of these, the exponents depend on x, are not constant. Sorry, are not constant. They depend on x. Is that making sense? So the idea of natural log is just to like to find the derivatives of these functions. The derivatives of these functions. We take natural log of both sides of the equation and then differentiate implicitly. We take natural log. And take and differentiate and take the derivative of both sides with respect to x. Okay. Well, I'm about to do that for like before, but let me give you a second first to copy this. Well, let's start with y equals 2 to the x. So let's say I want to find the derivative of this with respect to x. So find dy dx, which is the derivative with respect to x of 2 to the x. Okay, so we're going to learn how to do this. So again, the idea, well, let me put using logarithmic differentiation. So the strategy here is to take natural log to both sides of the equation. So if you take natural log of the left side, it becomes natural log of y. And if you take natural log to the right side, it becomes natural log of 2 to the x. Okay, so here you just take natural log on both sides of the equation. Okay, is this now the reason for doing that is that natural log has like properties when it comes to powers, right? If you go back to what I wrote a couple minutes ago. So how could you rewrite this using the properties of natural log? Yeah, let's go back so that everyone sees that. So if you look at the third property, the natural log of a power allows you just to bring the exponent outside the natural log. So in this case, the exponent is x, so the properties of natural log just allows you to write the x in front of everything. So you can just put x times ln of 2. Is that making sense? Okay, and then once you have the equation in this format, is not that different from what we have been doing a couple of times since the beginning of the class and all of yesterday. So you take the derivative of both sides of the equation with respect to x. Let me put it here. I'll put everything. I'll just keep. Okay. And then what's the deal here? You cannot find the derivative directly because this is in terms of y and this is with respect to x. So what you have to do is like again the chain rule trick of multiplying and dividing by dy. So you can put the derivative of natural log with respect to y times dy dx. And what should you do here? Well, ln of 2, that's just actually like a number. It's a constant. You don't know what the number is necessarily, but this is just a number. So you can actually take it outside the derivative. So you just get something like this. Is that making sense? Questions about this up to this point? Let me give this a different color for as usual. Okay, and now you have the formula for the derivative of natural log, which I wrote a bit earlier. So what's the derivative of natural log? Right, it's 1 over y. If you go back, it would be 1 over x if you had x, right? But here now we have y, and so you have to put y here. You see, so it's just like kind of like psychologically, it's the same formula. It's just that you have to change. We kind of change our minds about what the variable we are using is. But if when it's x, here you put an x, and if you have here y, then you have a y. So good. So you get 1 over y dy dx equals ln of 2, because remember the dx is just 1, right? It kind of cancels out as a fraction. It's not a fraction, but it behaves like a fraction in many ways. So, and this allows you to solve for dy dx, right? So you get y times ln of 2, right? But what is dy dx? I mean, this is the answer, but again, it's kind of weird because you have y on this side, and you kind of want to leave the answer in terms of x because the derivative is with respect to the variable x. So the only thing you have to do now is just remember what was the formula for y, and if you look at the formula for y, it was 2 to the x. Okay, so that means that the derivative, so to summarize, what that means is that the derivative with respect to x of 2 to the x is 2 to the x ln of 2. Is that making sense? Because y was 2 to the x. Okay, let's see, just to check if this is making sense. Let's try the next one. I'll give you a chance to do it on your own first. So like the next one was 3x squared plus 1. Okay, so the exponent is now x squared plus 1. So and the base is 3. So try to find the derivative of this one using this method, logarithmic differentiation. So it's exactly the same. You take ln on both sides, take derivatives on both sides, but I'll give you a chance to work it out. So let's take like a 6-minute break in case also you also want to go to the restroom or whatever. And then at 1:50, we just do it together and we can discuss it, if that sounds good. So it's like a break slash exercise. Resume the recording. Okay, let's see what this problem, the solution is like. So again, you start by taking natural logs on both sides. I'll start just to speed things up. I'll just use the colors when necessary. So you take natural log on both sides, so you get ln of y equals ln of 3 to the x squared plus 1. Okay? There's no simplification that you can do to the left-hand side. That's just ln of y. But on the right-hand side, you can use the property of log that it brings down the exponent. So the exponent in this case is x squared plus 1. So you put x squared plus 1 times ln of 3. Is that making sense? And after that, it is more or less indistinguishable from what we did in the previous example. So you take the derivative on both sides with respect to x. We cannot take the derivative on the left-hand side directly. We have to use the chain rule. And for this one, the ln of 3, that's just a number, it's a constant, so you can take it outside the derivative. So far so good. Any questions up to this point? And what is this thing? That's 1 over y times dy dx. And the derivative of x squared plus 1 is just 2x, so you get ln of 3 times 2x. Here you just have to be careful to make it clear that the 2x is not inside the like natural log. So you can write it in that way if you want. And so you solve for dy dx, which is y ln of 3 times 2x. But what is y? Y was 3 to the x squared plus 1. It actually looks a little bit better this way. And that's the derivative. Is that okay? I don't know how many tried to do it, but any questions about this one? It's really always all the same steps, every single problem. I'm just increasing the difficulty a little bit from one example to the next. But it does have the same strategy. Find okay, what was the next problem? X to the 2x plus 7. So find the derivative of this using find the derivative using logarithmic differentiation. So again, you literally start by taking ln of both sides. You get ln of y equals ln of x to the 2x plus 7. And again, there's nothing you can do on the left-hand side, but on the right-hand side, you use the property of ln to bring down the exponent. So you get 2x plus 7 here times ln of x. Okay? And now you take derivatives on both sides with respect to x. Oops. Is that making sense? Oops. Sorry, the ln of y. That's what happens to the left-hand side, right? You apply the chain rule one more time. And how do you find the derivative in this case? What should you do? You can use the product rule, good. So if you use the product rule, is the derivative with respect to x of the first factor times the second factor, right? Plus the first factor times the derivative of the second factor. Okay? So that's what the product rule says. So here I'm doing the product rule, correct? The difference is that now both factors depend on x. Before, one of the factors was always a single number. So that's why now we do have to apply the product rule. And everything else is more or less the same as before. This is 1 over y times dy dx. The derivative of the first factor is just 2 ln of x plus the first factor and the derivative of ln of x, remember, is 1 over x, so you can put the 1 over x at the bottom. So dy dx is y times 2 ln of x plus 2x plus 7 over x. So dy dx is, what is y? Y was x to the 2x plus 7. Okay. And that's the answer for this problem. Is that okay? Are there any questions about this? Okay, and again, let me kind of go in increasing level of difficulty. The hardest type is kind of the next one in this type of problems. So let's try the last one, which is let's go up. Sine of x to the cosine of x. So let's try it out. Let's try to find the derivative of that using logarithmic differentiation. So again, let's do the same thing as all the other problems. You take ln on both sides. So you put ln of y equals ln of sine of x to the cosine of x. Okay? Nothing that can be done to the left-hand side. And to the right-hand side, you use the properties of log to bring the exponent down. So the exponent in this case is cosine of x, so you get cosine of x times ln of sine of x. Is that making sense? And now you have to differentiate both sides with respect to x. And what's going to happen here, we're going to, on the left-hand side, we're going to do the same thing, which is the chain rule, right? And what are we going to do to the right-hand side? We're going to do the product rule again. Is that making sense? Any questions about this up to this point? So here's like the product rule. So this is just 1 over y, dy dx, right? What's the derivative of cosine? It was minus sine of x. That one is one you should definitely remember. And then how do you find this derivative? What would you do to find this derivative? Let's put it inside a box. Uh, Close, but not quite that. It is similar to that, but not that per se. Any other guesses? Well, actually, that one also is not it. We have to use it. It is a chain rule problem. Once we see it from that angle, the answer will be easier. So to think about it, right, yeah, everyone has like it's a hybrid in the sense of what you are saying. If you call u equals sine of x, right? This would be the derivative with respect to x of ln of u. Okay. And then that's a chain rule, so you put ln of u du dx. So it gives you 1 over u. What's the derivative of u with respect to x? What's the derivative of u with respect to x? That's cosine of x. And what is 1 over u? 1 over u is 1 over sine of x. So it is kind of like you bring the sine of x down, which is kind of what happens with the natural log, but you have to multiply by the derivative of sine, which is cosine. So the answer here is that it's cosine of x divided by sine of x. Is that making sense? So this is where this is like a tricky problem because of the chain rule. If you want, you can write it as cotangent. That's more up to you for these problems. But yeah, you could rewrite it as cotangent of x. Yes, that would also be fine. It's fine also just to write it as cosine divided by sine. I wouldn't mind either way for this problem. And the answer is almost there, except that you have to rewrite y in terms of x. So is that making sense? So they're kind of a mess. Like if you look at these answers, like it's not like an expression that you're necessarily interested in simplifying. It's just more like to test the skill of like, well, you apply natural log to both sides of the equation, you understand the properties of natural log, and things like that. But like these formulas by themselves, like they're kind of like they are a bit artificial. It's more like to show you like another way to create more like derivatives of functions. Is that okay? But they are always the same. That's why I wanted to do like, for example, so that you would see that they always behave the same way. Um, okay, so we don't have that much time left because we have the quiz at the end of class. So what I'll do right now is just give you a brief sketch of related rates, which is the last topic for the second exam. And then we'll do that tomorrow, and that would be where the exam ends. So let me just talk a little bit about related rates, like more conceptual stuff, and next time we'll do more of like applications and problems that involve them. And this is actually kind of like the first application of derivatives, so they're kind of like fun problems to work with. So let me write that down. So there are two things that I have to say that it's useful to keep in mind when we talk about related rates. So the first thing is a little bit more of like the visual interpretation of the derivative. So if you remember, let's say that the graph of your function looks like this. In fact, let me draw it more. Let's say that the graph of your function is like this. Now, we want to think of this graph as some sort of like hill or like a mountain. Think of this as some terrain that you're walking along. So let's choose 2 points here. So I'm going to take the point A. So this is the point A comma f of A, right? And let's choose another point, another value for x, which would be V. And so this would give us a point Q, which is B comma f of B. Okay, so so the tangent line for the point P will look like this, right? And this is more like conceptual analysis. What would you say is the slope of this line? Would you say the slope of this line is positive or negative? Yeah, the slope of this line should be negative. Okay, and if you imagine like this were like a hill that you're walking down, like this is a hill, you're walking along this hill, or like it's like a ball rolling, right? And you see like once you start moving like near this point, you're kind of like going downhill, right? So here when you're walking, if you follow the this terrain and you're walking near this point, you're going downhill, and that's related to the fact that the slope was negative. Okay, so here you're walking downhill. And what that literally would mean is like, for example, that your height, if you're, imagine this is kind of like the sea level or whatever. So that literally means that your height is decreasing, right? So the interpretation of the derivative, so like the interpretation of the derivative, let me put it right here. Is that if the derivative is negative at some particular point, then the function is decreasing there. Is that making sense? Any questions about this? No, but what can you say about the other point that I'm drawing for you? Let's say this point Q. If you look at this point Q, right? At the red point, the slope should be positive in this case. And like again, you have to imagine that, oops, you have to imagine that you're walking along this hill. And we always walk from left to right. I should have said that. But the convention is that you walk from left to right or west to east. So you're walking along this hill, and now as you're moving towards a point Q, right? If you have like a GPS or whatever, like something that's measuring your height, you would see that your height starts to increase, right? With respect to the sea level, which is like at like the x-axis, for example. So the interpretation of the derivative being positive is that the function is increasing near that point. So here walking uphill. So if dy dx is positive at some point, then the function is increasing at that point. Is that making sense? Near that point. So it's really like a roller coaster type thing. When you're going up, if you're on this cart on the roller coaster, as you are climbing along the roller coaster, as you're going up, the derivative or the slope is positive, and once you're going down, the derivative or the slope is negative. Is that okay? Are there any questions about this? And so, I mean, like, there's another thing I have to tell tomorrow, but I'll just probably say it next time because I don't want to. This could take a little bit more minutes than I want to. But so the idea is like tomorrow we'll interpret the derivative in different ways. So, for example, like the function could be something like the money that you have in your bank account. Okay, so that could be the function, and that function will depend on time because maybe today is Tuesday, you have some amount, you spend some money, then Wednesday you have a different amount, maybe Thursday you get some money deposited into your account, right? And then you have more money. So you can think of like the money in your bank account, as depending on time. So it would be a function of time. And so if you're losing money or you're spending money, right, like the money in your bank account is decreasing, right, it's shrinking, you have less. So the derivative of that function will be negative. But if you got a deposit and the money on your bank account is increasing, right, you have more money now to spend, then the derivative of that function would be positive because the amount that you have in your bank account is growing. So that's kind of the sort of thing how you end up analyzing many natural functions like that appear in the real world in terms like of calculus. So growth is related to positive derivative, and something shrinking or like becoming smaller is related to negative derivative and things of that sort. But again, I'll tell you more about that tomorrow once we get into related rates. So, yeah, if there are no more questions, let me make, yeah, so for the quiz, you have 30 minutes, although it should take you less time, but you feel free, you can now go and take it if you want. I'll see you tomorrow, and we'll finish tomorrow the material for the second exam. Okay.